So today I see another topic, which is kinematics. Kinematics. So kinematics is the
Yes, sir.
study of motion without considering the force responsible for the motion. Remember that um, for any object to move, force is required. For an object to move from one point to the other, force is required. You need to apply a force
Yes, sir.
to move or to lift an object from one point to another, from one location to another. So now when we study the movement of an object without considering the force responsible in moving the object from one location to another, such a study is referred to as kinematics. So that is what we are going to study here today. Now we talk about movement, that is motion. What is motion? Motion is change in position of an object over time. Change in position of an object over time is referred to as motion. Change in position of an object over time. That is motion. So when we talk about motion, there are 5 types of motion. 5 types of motion. The first is translational or linear motion. We can also call it motion in a straight line. Translational or linear motion, which can also be called motion or referred to as motion in a straight line. The second type of motion is random motion. Random motion. The third type of motion is oscillatory or vibratory motion. Oscillatory or vibratory motion. The fourth type is referred to as rotational motion, and the fifth type is referred to as circular motion. Circular motion. So let's look at them one after the other. So we look at translational or linear or motion in a straight line. So a translational or linear motion is the movement of an object in a straight line. When an object moves in a straight path, we call it a translational or linear motion. Example is a moving car. Another example is a person pushing trolley in a supermarket from one point to another along a straight line. And then a third example is a boy or a girl going to school. So these are three examples of a straight line or linear motion. The second type of motion, as mentioned before, is random motion. It is the movement of an object with no specific direction. When an object is moving in an unspecified direction, moving zigzag in zigzag manner, we say that such motion is a random motion. We have three examples there. The first is the movement of an insect. We have carefully observed the movement of an insect like ant, butterfly, mosquito, fly, in well-defined path. They move zigzagly. That is an example. Another example is the movement of gas molecules. We know that gas molecules moves randomly in their containing vessel. So gas molecule is also an example of random motion. And then when people go to market, you notice that their movement cannot be defined because they buy one item from one shop and then move to another point, buy another item, move to another point, buy another item. They keep moving up and down within the market from one point to another, sourcing for whatever items they want to buy. So by the time you put their motion together, you discover that you cannot define it. You only classify it as a random motion because their motion will not be straight. It will only fall within these type of motion, which is zigzag motion. Now, the third aspect or third type of motion is oscillatory or vibratory motion. It is a movement of a body about a fixed point, repeating itself in an equal interval of time along the same path. If you have seen a clock, a bell will give you this kind of motion, to and fro motion. Then simple pendulum is also another example of this type of motion, to and fro motion. When you observe a bird flying in the sky, you see the way it flaps its wing up and down. It shows equal interval of time. The time the wings goes up is equal to the time the wings come down. So it's a to and fro motion. Then another example is violin, that is string instrument. We have the guitar string, we have the violin, we have the viola, cello, double bass. Anything that has to do with spring will give us a vibratory motion. The fourth type of motion is rotational motion. That is when an object moves or rotates about an axis. We say that it is a rotational motion. Like an example is our ceiling fan. The blades of our ceiling fan rotates about a fixed point. And then our car tire, the wheel of our car tire moves about a fixed axis. So these are two examples of rotational motion. And finally, we have the fifth type of motion, which is circular motion. Circular motion is the movement of a body or an object in a circle at a constant speed. So rotational motion moves in a circle or ellipse and rotate about an axis. But for a circular motion, it's not rotating about an axis. Rather, it is moving at a constant speed. That is one basic difference between a circular motion and a rotational motion. Example of a circular motion is the motion of electrons around the nucleus of an atom. That is an example of a circular motion. And also we can say the movement of the earth around the sun is also a circular motion, or the movement of the moon around the earth is also a circular motion. Now, what is the difference between a circular motion and a rotational motion? A circular motion, the distance between the body's center mass and the axis of rotation is fixed, while in rotational motion, the distance between the body's center mass and the axis of rotation is not fixed. It keeps changing. So an example is this. Look at the Earth here. This is the Earth. It is moving around the sun. This is a circular motion. By the time it moves around, that is a day. Now, while the Earth is moving around the sun, it is also revolving about its axis. It is also rotating about its axis. So that is why you see this red line. The red line shows the axis of rotation. So the Earth is rotating about its axis and at the same time moving in a circle around the sun. So these are two typical examples of a circular motion and a rotational motion. So motion can be in one dimension, in two dimensions, or three dimensions. By one dimension, we refer to the motion of a body in a straight line along x-axis. X-axis is always horizontal, like a straight line along the x-axis, or it is moving vertically along the y-axis. or it is moving this way along the z-axis. So by one dimension, we mean that the object is either moving here, or is moving here, or is moving this way. It is not exhibiting, it's not moving in the three axes at the same time. One axis, that is, it is moving straight, horizontally, or it is moving upward. Take, for instance, a lift in a tall building. The lift is going up or is coming down. That is one dimension. That is moving vertically. And then another example is a car on an express moving. It is moving horizontally. It is not moving up. It is moving horizontally. So that is one dimension. Motion in one dimension. The object is moving in a straight line along the x-axis, or along y-axis, or along z-axis. So when we say object is moving in two dimensions, it refers to the motion of a body in the x-y plane. So in this case, the object is moving. The motion of the object can only be defined by this. So the object is going up at the same time it is moving away. This is the origin. This is the origin. The object starts moving up from here, and then it's also moving away from where it started. So when we have this kind of object, we say that it is two-dimensional object motion. Example is a basketball. When a basketball player throws the ball into the basket, the path it follows this way is referred to as two-dimensional motion. Another example is when a football player or a goalkeeper passes a ball upward this way. This is a two-dimensional motion because the ball is going up vertically. At the same time, the ball is moving away horizontally. So that is an example of two-dimensional motion. Now, the three-dimensional motions. Three-dimensional motion is referred to as the motion of a body, object, or particle in the x, y, and z plane. So this kind of motion is defined by the three components, the three axes at the same time, not separately. So an example is particle in space. Let's say a dust particle in the sky, or a bird flying in the sky. The way to define the motion of the bird is by this. Is by this. X, Y, and Z. So this is a three-dimensional motion. Now, reference frames. Any measurement of position, distance, or speed must be made with respect to a reference frame. This is simply telling us that if you want to make measurement, you choose a point as your starting point. So that point you choose as your starting point is your reference point. For instance, if you want to measure the length of the room where you are, you can decide to measure it from the door to the other end. You can decide to go to the other end and measure from there to the door. So reference frame is telling us that the point where you start your measurement should be considered as your reference point, which is your origin. So a reference frame is a region in space where observations and physical quantities are measured. Where observation and physical quantities are measured, a reference frame. For example, if you are sitting on a train and someone walks down the side, their speed with respect to the train is a few miles per hour at most. So if you have experienced this before, maybe you are seated in a car and people are standing by the roadside and then the car is moving away. If you look through the window, it will appear to you the trees, the human being standing by the roadside, and even the road where you are driving would appear to you as if they are the ones running away from you. You are just somewhere, but they are the trees by the road, the people standing by the road are the ones running away from you. Or if you look out to the ground, it will appear to you as if it is the ground that is running away from you. So that is how it appears. However, this is happening so because you and the other object are in different reference frames. You are not in the same reference frame. So to you, they are moving. To them, you are the one moving. Now, if you are in the same reference frame with someone, for instance, you are in a car, or both of you are seated in the car, you will not see that person moving. But those who are standing by the road watching your car drive past will see you and the other person as well moving. You are seeing that person in the car with you, not moving. But those who are outside the car will see that person moving as the car is moving. So that is what you need to know about reference frame, because this is happening because you are not in the same reference frame with the person outside the vehicle. Now, we've talked about the study of kinematics. We've talked about kinematics, which is the study of motion without considering the force responsible for the motion of the object. So, other physical quantities we can study alongside, since we are studying motion. Motion is change in position of an object. So when an object changes its position, it means that it will definitely cover a distance. And if it moves in a specific manner, it means that the distance it covers would be specified. And the time it takes to cover the distance, the rate at which it moves, all these are part of what we are going to study alongside with motion. So distance is how far an object travels from its original position. How far an object travels from its original position. It is also the length of the path traveled by a body Distance is categorized as a scalar quantity, and the unit of distance is meters. Smaller unit will be centimeter, millimeter, decimeter, micrometer, nanometer, picometer. But for the standard unit of measurement, distance is measured in meters. Displacement. Displacement is how far the object is from its starting point, regardless of how it got there. So while distance considers the paths the object travels, displacement does not consider the paths the object travels. The displacement only considers the starting point and the final point. So it is also defined as change in position, change in final position, and or the difference between the final position and the initial position. We can also define displacement as distance traveled in a specific direction. Distance traveled in a specific direction. Displacement is a vector quantity because remember that vectors are quantities that are defined by magnitude and direction, while scalars are defined by only magnitude. So distance is a scalar quantity because it is only defined by magnitude, while displacement is defined by the magnitude and the direction. That is, distance, which is magnitude, a scalar quantity, traveled in a specified direction. Direction has come in to it. So displacement is a vector quantity. However, the unit of displacement and distance is the same. They are both measured in meters. Now, characteristics of distance. It is the length of the path followed by the object in certain time. The path followed may or may not be along a straight line. It is a scalar quantity. It depends on the path followed by the object. It is always positive. It can be more than or equal to displacement. It may not be zero, even if displacement is zero. You need to note those points, very important. Now, characteristics of displacement. It is the difference between the final position and the initial position of a body. So when an object moves from one point to the other, the difference between the points, that is displacement, it is always along a straight line. It is a vector quantity. It is dependent on the path. It is independent on the path followed by the object. Distance depends on the path. Displacement does not depend on the path. Displacement may be positive, negative, or zero, but distance can only be positive or zero. It can never be negative because it's a scalar quantity. When distance is negative, it becomes displacement. It may be equal, but cannot be more than the distance traveled. It is zero when the distance traveled is zero. So now this diagram illustrates all the points mentioned in the characteristics of distance and displacement. So if you look at this diagram, the object started here and finished up here. It moved in this way, in this zigzag way. So if I want to find the distance, I will measure from here to here, measure from here to here. This will be this plus this. So if this is 1, this is 2, this is 3. That would be 1 plus 2 plus 3. Displacement will be the difference between the final and the initial. So let's assume that the initial here is 0, starting point. The final point here is 5. Final minus initial. Final is 5, initial is 0. So displacement is 5 meters. Displacement does not depend on the path followed, but distance depends on the path followed. So note this point. Now, 4 cases that we need to know about distance and displacement. When distance traveled and displacement are equal. Now, if an object moves 10 meters along the positive x-axis from rest and further moves 5 meters in the same direction, in this case, the distance traveled by the object is 15, and the displacement is also 15. So let's illustrate, let's see how it works out. The object started here and moved 10 meters and then continue for another 5 meters. 5 meters. So here is 10, here is 5. So this is the initial point, this is the final point. The total length traveled is 10 plus 5, which is 15. That is the distance covered. Now the displacement will be the final minus the initial. The initial is 0. At this point where it is 5, and then the full length is 15. So 15 minus 0 will give you 15. That is
okay, sir.
Displacement. Now, let's look at the second case. When distance traveled and displacement are not equal, and displacement is 0. I mean, displacement is positive. So if an object moves 10 meters long in the positive x-axis, this is, let's say this is 10, and further moves 5 meters in the opposite direction. So the object made a U-turn and moved 5 meters. 5 meters. So here is 10, here is 5. So 5 meters. So here is 10, and further move 5 meters in the opposite direction. So the object made a U-turn and move 5 meters. 5 meters. So here is 10, and further move 5 meters. 5 meters. So here is 10, and further move 5 meters in the opposite direction. So the object made a U-turn and move 5 meters. 5 meters. So here is 10, and further move 5 meters in the opposite direction. So the object made a U-turn and move 5 meters. 5 meters. So here is 10, and further move 5 meters in the opposite direction. So the object made a U-turn and move 5 meters. 5 meters. So here is 10, and further move 5 meters in the opposite direction. So the object made a U-turn and move 5 meters. 5 meters. So here is 10, and further move 5 meters in the opposite direction. So the object made a U-turn and move 5 meters. 5 meters. So here is 10, and further move 5 meters 5 meters in the opposite direction. In this case, the distance traveled will be the total path taken, that is, going around this way from beginning, coming to this final point. So this is 10 plus 5. That will give us 15 meters. That is distance traveled. But for displacement is final minus initial. If from the initial to this point is 10, and from this point to this point, the final point is 5. So the final point, F and I, F minus I will be 5 minus 0, which is equal to 5 meters. Because the final point here is 5. Here, the initial point is 0. So note that. And displacement are not equal, and displacement is negative. So in this case, if an object moves 5 meters along the positive x-axis, so it moved 5 meters initially, 5 meters, and then made a U-turn and moved 10 meters. 10 meters. So this is the initial position. The initial position is 0. From where it started is 0. Then where it ends is 10. That distance covered will be 15, because distance considers the whole path taken. So it will go all the way from the beginning 0 down to the end. So that will be 5 plus 10 will give you 15. 5 plus 10 will give you 15. Now, the displacement is final minus initial. Final minus initial. So if you look at this, where the 0 is, initially the object was going in the positive x-axis. Positive x-axis. So it got to 5 and then returned. So from this point to 5 and then back to 0 is also still in the positive x-axis. Remember your quadrant like this. This is your quadrant. If you recall your O-level, this is your quadrant: north, south, east, and west. So everything in the north side is positive, the south side is negative, the west side is negative, the east side is positive. So if I move from the center to the east and then back to the center, I'm still in the positive quadrant. I'm still in the positive quadrant. But once I cross this north-south pole, and move to the west, I have entered the negative quadrant. I have entered the negative quadrant. So this will be, my displacement will be 10. That is minus, the difference will be minus 5. Because from this point to this point is 5. From this center to this point is 5, and the 5 is in the minus axis. So we are going to have minus 5 as our displacement. And it's logical. You move one step forward and 2 steps backward. If you move 1 step forward and 2 steps backward, it means that you are in a negative side, -1. If you move 5 steps forward and then 10 steps backward, you are in a -5. So see it that way. Now the final one, when distance traveled and displacement are not equal and displacement is 0. So in this case, the object moves 5 meters along the x-axis and another 5 meters in the opposite direction. So 5 meters here and then 5 meters back. 5 meters going forward, 5 meters moving backward. The distance will be 5 plus 5, which is 10. But displacement will be 5 minus 5, which is 0. 5 minus 5, which is 0. So let's make progress. One general way of locating a particle. One general way of locating a particle or particle-like object in which a position vector r is with a position vector r, which is a vector that extends from a reference point, usually the origin to the particle. So this will bring us to 3 dimensions. 3 dimensions. So if I have an object in space or a particle in space, I can only define that particle by defining it in terms of the X, Y, and Z axis or components. So R there represents the position vector, while X, Y, Z represent the components vector, that is X-axis, Y-axis, and Z-axis. If you recall, when we treated vectors, we talked about this, the components of vectors. So now, if you look at that diagram, we have an object started here. An object was here at a particular time, and then it moved to this point. Let's say an insect or a bird in space. You could see a bird flying in the sky. The bird was here, you spotted the bird here at a particular time, and after some time, you saw the bird flew to this point. Now you want to find the bird displacement. Remember, displacement is equal to change in x, that is final minus initial. Let me write it properly. So displacement change in x is equal to final position minus initial position. So in the first position, initial position, we have written xi or ri. Since we are considering 3D. If we use x, it means that we are considering only the horizontal component. If we use y, it means that we are considering only the vertical component. And if we use z, it means we are considering only the z component. So to consider the three components together, which correctly define the position of an object in space, we are going to use R. So change in R is equal to R2 minus R1, or we can say R final minus R initial. So what is R final? That's the final position of the object. R final becomes X final, Y final, and Z final. R initial becomes X initial, Y initial, and Z initial. So if I write my position vector, that is my displacement, which is change in R, is equal to R final minus R initial. So that gives us, that implies that we are going to consider each of the components, the difference between the component X final and X initial, the component Y final and Y initial, the component Z final and Z initial. So that will give us our position vector. Our position vector or displacement of the object. So that is what you find here written. X two minus x1, that is x2 represent x final, x1 represent x initial. Then x is on the that is I component vector is on the x-axis, plus y final minus y initial, j component, plus z final minus z initial, k component. So that is how to use a position vector method to find displacement. Remember, displacement is change in position. Change in position. Look at it here. I have underlined, I have circled it. That is your displacement. Change in position. Final minus initial. final position minus initial position. That is your displacement. Don't forget it. So we'll move on to other quantities, speed and velocity. What is speed? When an object moves or change position from one point to another, speed must be involved. The rate at which the object moved from one point to another at a given time is what speed refers to. So the rate of change of distance with time is called the speed of the body. Mathematically, which is distance over time. The unit of distance is meters. The unit meter, the unit of time is second. So the unit of speed becomes meter per second. Now, speed could be uniform and it could be non-uniform. So what is a uniform speed? A body is said to move with a uniform speed if it covers equal distance in equal interval of time throughout its motion. Equal distance in equal interval of time. That is, the object, let's say, starts moving from 0 to 2 meters in 1 second. Then it moves from 2 meters to 4 meters in another 1 second. That is making 2 seconds. Then move from 4 meters to 6 meters in another 1 second, making 3 seconds. So if you notice that the distance between 0 and 2 is equal to the distance between 2 and 4, is equal to the distance between 4 and 6. That is 2 meters interval. So for every 2-meter interval, the time counts 1 second. So that implies that the speed is true. The speed is said to be non-uniform. Equal distances in the same interval of time. For instance, 0 to 3 in 1 second, then 3 to 4 in 1 second, then 4 to 8 in 1 second. So you notice that from the initial position to first position, that is 3 meters, 1 second. Then 4 to 8 is 4 meters in 1 second. So this is not a uniform speed. So average speed. There are 2 ways to measure the speed of an object. The first is the average speed, and the second is instantaneous speed. The ratio of the total distance traveled by the body to the total time of the journey is called average speed. Total distance traveled over total time taken is average speed. Another way of measuring speed is instantaneous speed. That is the speed of an object at a particular point in time is referred to as instantaneous speed. So this is the speed at a given time V dt is equal to ds of t over dt. So when a body is moving with a uniform speed, then the instantaneous speed and the average speed are equal. Note that point. It is very important. When the body is moving with a uniform speed, the instantaneous speed and average speed are equal. But if it is not moving at a constant speed or uniform, if it's not moving with a uniform speed, the instantaneous speed and the average speed are not equal. So velocity is the rate of change of displacement of a body with respect to time. Unlike speed the rate of change by distance and displacement. Distance is a scalar quantity. Displacement is a vector quantity. So all our definition of speed had to do with distance, because speed itself is also a scalar quantity. But now velocity is a vector quantity, which means we cannot use distance to define velocity, but displacement. So that is why we have it as the rate of change of displacement with respect to time. However, velocity and speed have the same symbol, v, the same symbol, v, and the unit is also the same, meter per second. Just like we mentioned before, uniform speed. Here we also have uniform velocity. When the magnitude and direction of the velocity of a body remains the same at any instant, then the body is said to have uniform velocity. For uniform velocity, acceleration is 0. And the contrary to this rule is non-uniform velocity. In this case, we have acceleration. For non-uniform velocity, there's acceleration, but for uniform velocity, acceleration is 0. We can also measure velocity in two ways: average velocity and instantaneous velocity. So average velocity is the ratio of the displacement to the total time. That is average velocity. And the instantaneous velocity is the velocity of a given body at an instant time, at a given time,
Hello,
at a particular time. Velocity of the body at a particular to the x over the t for x component, and for y component to be dy over the t over the t. Now, differences between instantaneous speed and instantaneous velocity. Instantaneous speed measures how fast time, how fast, take note of that, how fast a particle is moving at a particular time, while instantaneous velocity measures how fast a particle is moving in a specific direction at a particular time. Remember that velocity is a vector quantity, so it must always include, when you are defining it, it must always have a specific direction attached to it. So instantaneous speed, how fast the object is moving at a particular time, while instantaneous velocity, how fast the object is moving at a particular time in a specific direction. The next quantity is acceleration. The rate of change of velocity with respect to time is referred to as acceleration. A is equal to V over T. Acceleration is a vector quantity and the unit is meter per second squared. When equal changes takes place in velocity of a body in equal interval of time, then the acceleration is said to be uniform. One example is the motion of an object under gravity. That is why we have acceleration due to gravity G has a constant value of 9.8 meters per second square, because we have equal interval of equal changes in velocity at equal interval of time. The object is released and it's the velocity of the object at which the object is going up or coming down in equal interval of time is constant. So we have G to be 9.8 meter per second square, constant value. Now, for non-uniform or variable acceleration, when the changes in the velocity of the body in equal interval of time is not constant, when the velocity changes is not constant, then the acceleration is non-uniform. Average acceleration is defined as a ratio of change in velocity to the change in time for a given interval. So we have final velocity minus initial velocity over final time minus initial time. The ratio of change in velocity to change in time will give us our average acceleration. And for instantaneous acceleration, the average is the average acceleration in a limit, in the limit at the time interval becomes infinitesimally small. You can also say that instantaneous acceleration is the acceleration at a given acceleration of an object at a given time, at a specific time. At a specific time. So here we have A is equal to dV over the T. A is equal to dV over the T. So our time is past 1 hour. We are going to stop here. Tomorrow we are going to have another class. So we'll continue from this point where we stop from the tutorial. This is where we are going to stop our class today. Then tomorrow, we'll continue from here. Tomorrow being Friday, we'll continue from here. Thank you. In case you miss out at any point, I've sent the YouTube link to your class rep.
All right,
so
sir.
forward it to, or you forward it to your general platform.
Tutorial.
Go back
Okay,
and
sir.
go through